question that puzzled some of the greatest minds for thousands of years. You give a ball a good push, it rolls for a bit, and then it just stops. Why? Why doesn't it just keep on rolling forever?
For the longest time, the answer seemed pretty obvious. The big idea was that everything just wants to be at rest. That was its natural state. Motion? That was seen as a temporary thing, something that would always wear out. It kind of makes sense, doesn't it? It just feels right.
And that one simple observation, that gut feeling, became the foundation of physics for centuries. It created this huge mystery, a whole field of science built on an idea that was intuitive, but, well, deeply flawed. And this, right here, is where everything we thought we knew gets turned on its head. That gut feeling, that common sense that drove science for ages. Turns out it's completely wrong. An object's natural state isn't rest at all. The real truth is hiding in these invisible forces that are at play all around us all the time.
So, what are these invisible things pulling the strings? Well, it all comes down to a really revolutionary idea: unbalanced forces.
First things first, what exactly is a force? I mean, we can't see it, but we feel its effects constantly. To put it simply, a force is just a push or a pull. It's the effort you put in that can change how something's moving, what direction it's going, or even its physical shape.
But here's the absolute key. Not all forces are created equal. You've got balanced forces. Think of a game of tug-of-war where nobody's winning. The forces are equal, they cancel out, and nothing changes. But when one force is stronger than the other, you get an unbalanced force. And that is the secret ingredient, the one thing that actually causes a change in motion.
Let's make this real. Imagine you're trying to shove a heavy box across a carpet. You're pushing, you're applying a force, but for that first second, absolutely nothing happens. What's going on?
It's because you're not unopposed. There's an invisible force fighting back against you: friction. The floor is literally pushing back with an equal and opposite force, creating a perfect standoff. The forces are balanced, and your push gets completely canceled out.
So here's the breakthrough moment. The box only starts to slide when your push becomes stronger than the force of friction. At that exact instant, the forces become unbalanced, and it's that leftover unbalanced force that finally gets the box moving. This one idea completely shatters thousands of years of old thinking.
And this powerful idea leads us straight to the first great law of motion, a concept really championed by the one and only Isaac Newton, the law of inertia.
So what is inertia? Honestly, you can just think of it as an object's stubbornness. Or maybe it's laziness. If an object is sitting still, it wants to stay sitting still. If it's already moving, it wants to keep moving, just the way it is. It will literally resist any attempt to change its current situation.
And trust me, you've felt inertia your entire life. When a car slams on the brakes, the car stops, but your body's inertia wants to keep right on going forward. When a bus suddenly takes off, your body wants to stay put, so you feel like you're being thrown backward. That resistance, that feeling of being pushed or pulled, yeah, that's inertia in action.
So, how much inertia does something have? How stubborn is it? It all comes down to its mass. A massive freight train has way more inertia than a little shopping cart. And that's exactly why it's so incredibly hard to get a train moving in the first place, and even harder to get it to stop.
Okay, so we know an unbalanced force is what it takes to overcome that stubborn inertia. But the next logical question is, how much does it change the motion? That's what the second law is all about, the beautiful connection between force, mass, and acceleration.
Now, to really get this, we first need to understand the idea of momentum. It's actually pretty simple. It's just an object's mass multiplied by its velocity. So a cricket ball moving at high speed has a lot of momentum. A huge truck rolling along slowly also has a lot of momentum, but for a totally different reason: its incredible mass.
So here it is, Newton's second law. Okay, that sounds a little formal, right? Let's translate. All it really means is that the more force you apply to an object, the quicker you can change its momentum, whether that's speeding it up, slowing it down, or just changing its direction.
And this whole powerful concept gets boiled down into maybe the most famous equation in all of physics: F equals ma. Force equals mass times acceleration. It's just so simple and elegant. It tells us that if you want a big acceleration, you're going to need a big force. And if you're dealing with a really massive object, you'll need an even bigger force to get it to accelerate at that same rate. Let's see this play out in the real world. Think about a fielder catching a cricket ball. They never just hold their hands still, right? They always pull their hands back as the ball comes in. Why do they do that? Well, they're cleverly using the second law to their advantage. By increasing the time it takes to bring that ball's momentum down to zero, they're decreasing the rate of that change. And a smaller, slower rate of change means a much, much smaller force of impact on their hands. It's the difference between a great catch and a trip to the hospital.
So, we know how forces get things moving, but there's one last crucial piece of this puzzle. Forces never, ever act alone. And this brings us to the third and final law of motion.
This is Newton's third law, and it's pretty profound when you think about it. It means that for any force, any action that exists anywhere in the universe, there's another force, a reaction, that is exactly the same size and points in the exact opposite direction. No exceptions.
Now hold on. This is the part that trips a lot of people up. If the forces are equal and opposite, why don't they just cancel each other out so nothing happens? Well, here's the crucial detail. They always act on two different objects. Your foot pushes on the road, and the road pushes back on your foot. They're a pair, but they're affecting two separate things.
Think about it. When a gun is fired, the gun pushes the bullet forward. That's the action. The reaction is the bullet pushing the gun backward, and we feel that as recoil. When you walk, your foot pushes the road backward, and in reaction, the road pushes you forward. It's this beautiful, invisible dance of paired forces happening everywhere, all the time.
All right, let's zoom out and put this all together. These three simple laws completely rewrote the rulebook. They replaced thousands of years of wrong intuition and gave us a brand new, incredibly powerful way to see and predict how the physical world actually works.
So here they are, the three fundamental rules of motion. Rule 1, objects are stubborn. They have inertia. Rule 2, if you want to overcome that stubbornness, the force you need depends on the object's mass and how fast you want it to accelerate. And Rule 3, you can't ever push on something without it pushing right back on you.
So the next time you see a ball roll to a stop, you won't just see an object getting tired and returning to its natural state of rest.